Thanks for watching, and today I want to prove the famous Picard-Lindelöf theorem, which says that under certain conditions, ODEs do have, at least locally, a unique solution. And so, the name Picard means a lot to me because I know in France you have this delicious food called, Picard congelé. It's very good, so highly recommended. Alright, but anyway, what does Picard-Lindelöf say? It says the following. Suppose you have an open subset of Rm. So U and Rm is open. And you have some function that maps this set U to all of Rm. And suppose it is Lipschitz. So that's a very important condition, which will be, I'll talk more about that at the end. So suppose it's Lipschitz. It means it satisfies the following. F of x minus f of y is less than or equal to a universal constant times x minus y. So for all x and y in U. In other words, the difference of the outputs, it's uniformly controlled by this constant L. So it's sort of like continuity, but better. Continuity just means those two things are very close, but what this says is they're uniformly close in some sense. So I call it sort of linear continuity in some sense. Then, what do we have? Then, given some initial condition, x naught in U, so suppose x naught is sort of our initial thing, we can always solve a certain ODE locally. So given it, then there exists a unique solution, gamma, for minus tau to tau to U, and for some tau positive. So around time 0, we can always solve the following ODE of gamma prime t equals to f of gamma t with initial condition x naught. So if you give me an initial condition x naught and your function is nice enough, we can always find a solution of this ODE that is initially at x naught. So you can always find some trajectory gamma that goes to x naught initially. And that's defined on some small time interval minus tau comma tau. And in fact, we'll find an explicit calculation of this time interval. So very classical theorem. If this doesn't exist, then the ODE world would be screwed. So thank God this exists. Okay, and I like it because actually the proof is super neat. So it involves actually it involves the Banach fixed point theorem, and in fact there either already is video on this or I will make a video on that. So here's the proof. So first of all, let's prep some stuff. What is the main idea? So notice, we can actually take this ODE and integrate it. So in fact, we can turn from a differential equation to an integral equation. So let's take that and integrate it over the interval 0, t for some t. Then what do we get? Then we get integral from 0 to t of gamma prime t equals, I guess, let's use some different variable, gamma prime s ds equals to integral from 0 to t of f of gamma of s ds. Then what does that become? This just becomes gamma of t minus gamma of 0 equals to the integral from 0 to t of f of gamma s ds. But remember, gamma of 0 is just x naught. So what we really have is, as I said, an integral equation. Gamma of t equals to x naught plus integral from 0 to t of f of gamma s ds. And this is actually the formulation that we'll use in a second. And the reason this is nice is, I don't know if you've taken analysis, but one thing about analysis is that it's very hard to pass through limits. I think that class teaches you to be sort of scared of math. So in particular, if you have derivatives, it's super hard to pass through limits. Yet, if you have integrals, it's actually easier to pass through limits. There's some nice theorems, and in fact, we do want to talk about limits in a second. But let's again do some more prep work. So that was the motivation, turning the differential equation into integral equation. And now let's do some prep work. So prep. So let's define a couple of things. So first of all, f is Lipschitz, and if you do a simple epsilon delta argument, you find that f is continuous. So since f is continuous, we can actually find a compact neighborhood around our initial condition. So there exists a compact neighborhood because the idea is, well, f might blow up, but we want to say around x naught it doesn't blow up. So there exists a compact neighborhood. Let's call it N. And so it's just the ball centered at x naught and of radius r. Closure of that, so the closed ball, such, and a constant m. Such that f is bounded. So f of x is less or equal to m for all x in n. Actually, it's silly because in fact, this holds for every closed neighborhood. So, whenever you take a closed ball around x naught of radius r, f will be bounded. Because continuous functions on compact sets, they attain maxima and minima. And so that's why I don't really define r. It holds for any r. Of course, the constant m might change, and I think the bigger you let r, then the smaller your tau will be at the end. So just think of r as equal to 1, if that bothers you. And let tau, again, what is tau? It's the tau in the interval minus tau tau, where your solution is defined. I'll let it to be announced. So let this be a big time that's to be announced, and I will give you conditions soon-ish, okay? But what's important is, the bigger r is, the smaller your time is, and everything. All right, and now, as usual analysis, we want to have a space to work with. Now, let's just consider the following space. X is just the set of continuous functions defined on this small interval with images or outputs in n. So, again, you have this small interval where your solution is defined, and you map it to n, which is again a ball of radius r. And so you just want to find functions gamma that go from this small time interval into your space. That's great, we have this space, it's still abstract, but let's make it into a metric space. So let's just define a distance on that space. So And usually for continuous functions, a nice metric is a uniform metric. So d of the distance between two functions, you just let it to be the biggest pointwise distance. So supremum on the interval minus tau tau of the biggest absolute value, gamma of tau t minus sigma of t. So if you have two functions, the biggest distance, the distance between those two is really literally the biggest pointwise distance there is. This is gamma and this is sigma. And you'll see exactly here the supremum is attained. So that would be called the distance. And one thing I will not show, but it turns out with that distance, X becomes a complete metric space, and we'll need that. So X is complete. But let me just tell you a couple of words about the proof. It's very neat. If you have a Cauchy sequence, Fn, then for every X, just by this definition, Fn of X will be Cauchy. And because Fn of X for fixed X is just a sequence of real numbers, this number converges to some other number, and that number you call it f of x. And then what you do, use an epsilon argument to show that, in fact, with this metric, your functions fn converge to this function f. And you also have to show it's continuous and stuff. So it's a neat proof, but that's not why we're here today. Today we're here about ODEs. And now let me remind you our integral formulation, which is very important. Remember we had this. Gamma of t is x naught plus integral from 0 to t of f of gamma of s ds. And what we want to do, we want to set it up as an iteration scheme if you want. So let's just focus on the right-hand side. Notice it's a function of gamma. So let's just define t of gamma. It's a new function, whose input is t, and it spits out x naught plus integral from 0 to t of f of gamma s ds. So again, it takes gamma as its input, and it spits out this new function of t. So its input is a function, its output is also a function. And here's the clever observation of today. Suppose t has a fixed point. If t of gamma equals to gamma, then by this definition, and let me box it, it's super important, we would have that gamma of t equals to x naught plus integral from 0 to t of f of gamma of s ds. In other words, in fact, it's equivalence. In other words, solutions to ODEs are just fixed points of this operator t. So what have we done? We took this ODE, turned it into an integral equation, and in fact turned it into a fixed point problem. And who says fixed point? Probably says Banach fixed point argument, because we're not in the Schauder or Schaefer world or Brouwer world. Lots of fixed points. So today what we're going to use is the Banach fixed point argument. And I've done a video on this. So Banach fixed point theorem. So if you have a complete metric space, XD is complete, which we've shown already. X was the space of continuous functions. D is the the supremum metric, and T goes from X to X is a contraction. all this means is that if you take, for example, if you have t of x and t of y, and you measure the distance, it's always uniformly smaller to x and y. So t of x and t of y is always smaller than x, the distance of x and y, for some universal constant q that's less than 1. So suppose you have a complete metric space and you have a contraction, then a t has a unique fixed point. Then t has a unique fixed point. In other words, there exists a unique point such that t of x equals to x. Okay, and as I said, this is the crux of the proof. All we need to do is apply the Banach fixed point theorem. So what do we still have to show? We've already shown this is complete. We just have to show two more things. First of all, that t indeed maps x to x, and we have to show that it's a contraction. Once we've shown those two things, we're done. Because again, then t has a unique fixed point, and therefore a unique solution to our ODE. So, let's now show that t goes from x to x. Because all we know is that t, it maps, continuous function to a continuous function, but we don't know yet that it's, close enough to our initial condition. So, suppose gamma is an x, which again is a set of continuous functions from minus tau tau to the space n. And let's see what's going on. So again, I want to emphasize gamma is defined on that interval with values in n and then continuous. And remember that n is just centered at the initial condition of some radius. Okay, then let's look at t of gamma of t. Question is it still continuous, and is it still defined on minus tau tau with values to n? Well, let's see. Well, it's defined like that, right? Now remember, gamma is a continuous function. F is Lipschitz, therefore continuous. So f of gamma is continuous. And if you're integrating, you actually make it even better. So this is definitely continuous, and therefore the right-hand side is continuous, and therefore t of gamma is continuous. So the continuity is not a problem. Continuous. In fact, you can say more than that, it's differentiable. So definitely continuous. So all that's really left to show is whether, if you take this, the output is in n. So let's just show that t of gamma of t is in n, which again, it's just a ball centered at our initial condition. So, if you want a little picture, this is x naught, and maybe this is r, and we want to show that t of gamma t is somewhere here. Okay? So what we have to show essentially is just the distance between the two is less than r. Remember, we're in Rn, so, or Rm, so really this ball is with respect to the distance in Rm. So really what we have to show is that the Euclidean distance between the two is less than r. So let's calculate t of gamma of t minus x naught. And remember, we want this to be less than or equal to r. And now let's just use the definition. So it's x naught plus integral from 0 to t f of gamma s ds and minus x naught. So that was the definition of t, and that was because we do minus x naught. So magically, how nice, this cancels out, and you're left with the integral from 0 to t of f of gamma s. Yes. Well, we have an absolute value of an integral, so it would be nice if we could just estimate it by the triangle inequality, which indeed we can, because math is awesome. So this is less than or equal to absolute value integral of the absolute value of f of gamma s ds. And now remember what we had at the very beginning. Well, f is defined on that ball and it has maximum value capital M. So remember, so gamma of s, right, it's an n. And the reason we define this n is because f is less than or equal to capital M on this. So indeed, f of gamma of s, it's less than or equal to capital M. So this whole thing here, it's less than or equal to the integral from 0 to t of capital M ds. Well, it's just a constant. Antiderivative of m is ms. So this is equal to mt. Whenever your life feels empty, think of mt. And remember, what was t? It's less than or equal to tau. So, because t was defined on minus tau tau, so it's less than or equal to m tau. And remember, what do we want? Ideally, we want this to be less than or equal to r, because that's what we had at the beginning. We wanted to show that the distance between those two quantities is less than or equal to r. So that's what we want. But remember, we still had some leeway in defining our tau. So let's use that now. Just define tau such that this quantity is less than or equal to r. So define tau. Find tau such that just m tau is less than or equal to r. And that's why I said, the bigger you choose r, if the bigger you choose r, probably m will be humongous, so tau will be smaller. So just be careful. And therefore, what do we have? We have that, in the end, t of gamma of t minus x naught is indeed less than or equal to r. And why did we need that? It's to show that t maps x to x. So t maps functions which are r close to x naught into functions which are r close to x naught. So it's very good. You do have a, I think it's called an operator or something where it maps into itself. That was the first thing, and now let's prove the other thing, which is the contraction property. So step 3. In fact, the last step. So what we want to show is that this thing holds. So let's take two functions, gamma and sigma, and let's show that t of gamma and t of sigma are closer than gamma and sigma. So want we want this to be less than or equal to some fixed constant of the distance of gamma and sigma, where q is strictly less than 1, of course, greater or equal to 0. Okay, and let's just play around with this using the definitions. So what was D? It was the sup metric. So this is really supremum over T, again, in minus tau tau, of T of sigma, sorry, T of gamma of T minus T of sigma of T. Okay, now let's just unravel the definitions. So that's supremum over T of x naught plus integral from 0 to T. Oh, did I use? Yeah, that's fine. Integral from 0 to T of gamma of S, f of gamma of S, ds, minus the same thing but with sigma. So minus x naught minus integral from 0 to T f of sigma of S, yes. Lo and behold, the terms x naught cancel out, and what you're left with is supremum over T of the integral from 0 to T of f of gamma S minus f of sigma S ds. Of course, again, I know you want to, so let's do it. Let's put the absolute value inside the integral. Integral from 0 to T f of gamma S minus f of sigma S. What do we want to do next? Well, ideally we would like this T to disappear. But notice what we have. We have this quantity. It's non-negative. So the bigger T is, the bigger this integral actually becomes. So in fact, this integral attains its maximum at tau. So you have something like that, where let's say this is 0 and this is T. And you want to figure out, well, which T gives you the biggest area under this positive function? Well, it's at its biggest value, which is tau. So in fact, the biggest integral happens at tau. So this becomes f of sigma of S, gamma of S minus f of sigma of S ds. So now, what do we want to do? Ideally, we want to pull this outside of the integral. But in fact, we can do this because what do we have? This integral is less than or equal to the integral from 0 to tau. Well, this thing, by definition, is always smaller than its biggest value. So, and the biggest value, by definition, is the supremum. So let's call this supremum of S prime from 0 to tau of this function, f of gamma S prime minus f of sigma S prime ds. And what's nice, this supremum doesn't depend on S anymore, so we can just pull it outside of the integral. Oh, nice. And basically still have a tau up here. So this is supremum S prime between 0 and tau of f of gamma of S prime minus f of sigma of S prime, absolute value, times the integral from 0 to tau of ds. And instead of using S prime now, let's just use S. So supremum S in 0 tau f of gamma of S minus f of sigma of S, and then this integral is just equals to tau. Okay, so what have we done? We've shown that T of gamma minus T of sigma, at least distance-wise, is less than or equal to this quantity, But ideally what we want to do, we want to compare to the distance between gamma and sigma itself. So the thing that's very, very bothersome is that we have this extra factor of f, and the question is, how can we get rid of it? Well, there is one assumption that turns out to be really crucial that we haven't really used yet, which is the Lipschitz assumption. Remember that f of x minus f of y is less or equal to L times x minus y. So this thing, in fact, it's less or equal to the supremum from 0 to tau of L times the difference of inputs, which is gamma s minus sigma s. And then all this times tau. Well, this L and tau, we can put that together. So that's L tau supremum of s from 0 to tau of gamma s minus sigma s. Okay, and let me just see how I define things. Well, look, this is a small interval, 0 to tau. If you make it bigger, then this, wait. Yeah. Look, this is a small interval. If you make it bigger, then the maximum can just increase. So in particular, this thing then becomes less or equal to the supremum from minus gamma to gamma of this quantity. Less or equal to L tau supremum. S comes from minus tau to tau. Did I just say gamma? No. Minus tau to tau of gamma of s minus sigma of s. And why did I do this? Because if you look back at the very beginning, you probably recognize that as a distance of gamma and sigma. Okay, so what have we shown? We've shown that the distance of t of gamma and t of sigma is less or equal to L tau of the distance of gamma and sigma. In order to have it a contraction, in order for it to be a contraction, we need that quantity to be strictly less than 1. So that's what we want. And again, here's the cool thing. We still actually have some leeway of choosing our tau. So simply choose tau such that L tau is less than 1. And that's completely fine because the other selection we had was M tau is less or equal to R. So in fact, we can choose tau to be so small such as simultaneously M tau is less or equal to 1 to R and L tau is less than 1. So it's fine. And once we have that, we indeed get that T is a contraction. So we get that T is a contraction. So by the Banach fixed point argument or theorem, T has a unique fixed point. Fixed point, that is, T of gamma equals to gamma, and therefore we have a unique solution of our ODE. So there exists a unique solution of gamma prime equals to f of gamma. Or gamma initially is x naught. And our theorem has been proven. How neat is that? What did we do? We took our ODE, we rewrote this as an integral equation, we define this operator t that took the essence of their equation, and we just showed that this operator has a fixed point. And therefore we have a solution. And I just want to say two more things about this. So, remarks. Two things. First of all, so the Lipschitz condition, where did we use? Just at the very end. So you might think that it's not important, but in fact it is super important, because if your function is not Lipschitz, you might not have a unique solution. So, and for this I want to consider the following example. Okay, so Lipschitz is important. Consider y prime equals to square root of y, where y of 0 equals to 0. Square root is not Lipschitz near 0, because if you estimate square roots near 0, the difference, it's not proportional to the difference of the inputs. And in fact, turns out there are many solutions of this, because, well, 0 is a solution. Because if you take square root of 0, that's 0. If you take 0 prime, that's 0. And it's 0 at 0. But also, the following is a solution. Yt equals to t squared over 4. And you can get it by solving the ODE. And why is that? Because y prime of t, that's t over 2, so 2t over 4, and that's t over 2. But that's also, at least for t greater or equal to 0, that's square root of t squared over 4, which is square root of y. And indeed, turns out you can construct infinitely many solutions that start at 0, namely the following. For every c greater or equal to 0, the following is a solution. Y of t equals to, I guess, t minus c squared over 4 for t greater or equal to c, and 0 otherwise. In other words, the graph looks like this. From c on, this just becomes a parabola, and for c, for times less than or equal to c, it just becomes 0. And for every c, it turns out this is a solution, simply by the same argument here. So this ODE has infinitely many solutions for the same initial condition. So be super, super careful. I might be wrong, but I believe for continuous functions, solutions always exist, but they're not unique. And not only that, so I told you that locally the solutions exist, but it's definitely not true that the solutions exist for all time. And so let me give you another example. So let me talk very quickly about blow-ups. Consider the following example. Y prime equals to y squared with initial condition at 1. At least around 0, this function is Lipschitz. So indeed, around 0, there exists a unique solution. And in fact, if you solve it, and may have done this in another video, you get that y of t is minus 1 over t minus 1. Is a solution because if you differentiate this, you get 1 over t minus 1 squared, which is indeed y squared. And y of 0 is minus 1 over minus 1, which is 1. So this is indeed a solution, and it's a unique solution near 0, but of course if you graph this, then at 1, what happens at 1? Well, the solution blows up. So it looks like this. So you see this ODE, even though at 0 it's 1. Notice it blows up in finite time. As t approaches 1, it actually blows up to infinity. So, be careful. First of all, this theorem, Lipschitz, is important, and moreover, it just guarantees local existence. It doesn't guarantee that it exists for global time. Just a cautionary tale, but I hope you like this little ODE/analysis excursion. And if you want to see more math videos, please make sure to subscribe to my channel. Thank you very much.